Dave coming at you with a little lecture. Just going to be a quickie here. This is a flyer that I received from Ronin County for like the credit union for teachers, the bank for teachers. And I had a picture of like, oh, teachers doing stuff. And I was struck by like, first of all, this is a really complicated molecule that this teacher is explaining. And secondly, these kids seem really young to be doing molecular modeling. I don't know what elementary school you guys went to, but I don't remember molecular modeling happening, until now, like chemistry time. Speed limits. They post the speed limit. Technically, you can get pulled over if you're driving the speed limit, because the speed limit is actually the maximum safe speed under ideal conditions. So if it's night and you're driving 25 and a 25, you are technically not in ideal conditions and you could be pulled over. This would be a hard set of speed limits to follow. I think this is like some crazy school zone or something that has this speed limits at all these various times. And one thing that's like the speed limit is the octet rule. Let's think about zinc's electron configuration for a second first. Okay, zinc. Find that puppy on the poops. That's Na. Find zinc on your friend the periodic table. It is element 30. It will use an abbreviated electron configuration, so we're going to start with argon in brackets, and then after argon we're in the 4s, and the 4s can take 2 electrons, as you guys recall, and then after that is the 3d, and the 3d can hold 10 electrons because argon is way over there on the far side of things. How many valence electrons does this thing have? Okay. If you think about it, this has 12 valence electrons is one way of thinking about it. Some say that it just has these 2, but it has a lot of electrons going on. Okay. Is this something that's going to be bound by an octet? No. Okay. It has the possibility of having more. Why? Because it has the d electrons. The presence of being able to put electrons in a d orbital gives it the chance to have more than just the octets. If you're limited to S2 and P6, which is true for like if you're in the second row, you're only limited to a max of 8. But when you start having the access to go into the Ds, you can get more than 8. When do we start seeing the D? Well, as you can see here, it shows up at the 3rd energy level. So things in the 3rd row can potentially put electrons in the D. They're a big enough circle. Small circles don't have that much space. Medium circle, maybe by the time you get to like the 3rd energy level, there's room there for more electrons. If you think about the periodic table and who actually follows the octet rule, okay? Hydrogen only gets 2, so that one doesn't. Same thing with helium. That row doesn't really work that well. You never get like these things, lithium, beryllium, they never get up to 8. Same thing with these things here. They can never get all the way up. Once we're down here, as we've just seen with like zinc, things can be seriously expanded. So these ones don't necessarily play by the octet rule either. Things here are in the 3rd row. 3rd row elements like phosphorus and sulfur, they can potentially access the 3D. So these ones don't do it either. Boron always stays with just 3 electrons, so it only gets up to 6, so that one kind of fails. And so then the only ones that really are bound by the octet rule, we'll switch up the colors here, carbon, nitrogen, oxygen, fluorine. Now, as it happens, these 4 elements make up like 90% of your body, 90% of the air, 90% of a lot of things. And so therefore, we use the octet rule because so many of our compounds are ruled by those. But it is possible to have things, and I'll say neon would do it. We don't get into a lot of compounds with neon. But it is possible to have an expanded octet. And that's what we're going to see here. Just like the speed limits are only really followed by like your grandmother, maybe, most of the elements on the PT can have other than 8 electrons. Again, It's going to be a good enough rule. It's going to work for the compounds you're going to see, but I'm just going to show you today some things having more than 8 electrons and some compounds like that. So we're going to make this table again, this table that you had in your notes when you're first learning the shapes, and we're going to start with having 5 groups of electrons. 5 groups, 2 electrons in a group, we're going to have 10. So right now just go ahead and make the table briefly. I'm not gonna expect you guys to be able to like make strings to do these things like we would do if we were in physical class. So instead, I'm gonna show you an example from the molecule maker. Okay, here is something with 5 groups of electrons around it. One thing you'll see is that right away we've got some angles that are 90. These are 90, but then there's a different thing where there's another shape in here. Let me see if I can get it to show you this. Here's another shape. These are at 120. So this has 2 different shapes in this molecule. It's got 3, 1, 2, 3, that are flat in a plane at 120, like a trigonal planar. And then it's got these 2 that stick straight up and down like a linear. And the name of this thing is trigonal bipyramidal. Let's go ahead and do that nice and large in our notes. Okay, so the angles, there are 2 angles. Oops. There are 2 angles, 120 and 90. The shape has the name trigonal bipyramidal, and if we're going to try and draw it ourselves, we're going to get a picture that looks something like this. 3 of them flat in a plane at 120, 120, 120. I'll reinforce those. Oops, that's blue. We get a different color. So there's some that are flat in the plane here, and then there's 2 that go straight up and down. So the 120 angles are here, and then there's some 90-degree angles going straight up and down. Here is a compound that does it. Phosphorus pentachloride. Phosphorus starts with 5 electrons, okay, based on its position on our friendly periodic table. And then it bonds each one of those to a chlorine, and we get this compound here. Looks like a white crystalline powder, not a big deal. Not super interesting in itself, but this is an example of something that makes a trigonal bipyramidal structure. 6 groups of electrons. Think for a minute about 6 groups of electrons, pack it in there. The angles are going to be getting smaller as we go, and we have to like squeeze in from the like 109.5s that we were before. This one I'll show you with the model kit player with our device from FET Interactives. Okay, I'm going to add one more bond. There it is. And you'll notice the number that comes up here is now 90. If I tweak it around, it gets out of that, but eventually it drops back to 90 degrees. This is an octahedral molecule. This is like the things we did with the p orbitals, up, down, side to side, and down the plane. It is all 90 degrees, and again, the shape is octahedral. This is the only other shape you're going to need to know. You're going to have to add these 2 to our repertoire of possible molecules. So we have trigonal bipyramidal and octahedral that are now possibilities. Again, this is like what the p orbitals did, going in all sorts of opposite directions, groups of electrons trying to stay apart from each other. This is the kind of angles and shapes they make. Selenium hexachloride would do this. Molybdenum hexacarbonyl groups, I'm not sure what you call that one, but it is another example of something that makes these sorts of shapes. We do not need to worry about this. This is just some review, but we got another review exercise planned. Thank you for your attention. We will now end this screen recording. Hope you enjoyed it.